Yeah, so hello everyone and welcome you all in the fourth problem solving class of the course Principles of Signal and System. I am Vivek Kumar Srivastava, a PMRF research scholar of Antenna and Microwave Research Laboratory, Indian Institute of Technology, Roper, and TA of this course. So, in the previous class, we have seen uh, LTI system, that is linear time invariant system. Then we seen impulse response followed by convolution theorem, and at last we have seen linearity, causality, stability criteria of linear time invariant system. Whereas the topic of the today's class is Laplace transform, various properties of Laplace transform, and the inverse Laplace transform. So let us start. So first of all, before starting this Laplace transform, we have to understand that what is the need of learning this Laplace transform. So basically, as we know that whether it's the electrical circuit or it's the electronic circuit, is it is basically made up of the basic circuit component, that is resistor, inductor, and capacitor. Okay, so let us suppose this is my system. This is my system. Okay, so on this system, which is composed of resistor, inductor, capacitor basically, so on this system I am applying a signal which is equals to x of t. So once I apply this signal x of t to this system, so we will get some output from this system which is denoted as y of t. So basically in the previous class we have seen that the relationship between this input and the output of this system is basically described in terms of differential equation. Okay, so differential equation. Okay, so input relationship between input signal and output signal is basically defined by this differential equation. So for solving this differential equation in the previous class we have seen that it requires mathematical tools such as integration so as to solve this differential equation. Okay, uh, so basically this solution that requires mathematical tools, that is integration, it's a very complex. Like in the previous class we have seen that it is very complex to get a solution. Okay, by using integration. Okay, so basically Laplace transform is a tool that enables us to solve this differential equation which is very complex. Okay, or say higher order differential equation. So what this Laplace transform do, it basically enables us to to solve the differential equation which is defined in time domain by converting this time domain differential equation into frequency domain. So basically Laplace transform is a frequency domain analysis. Okay, so by using this Laplace transform we can easily reduce the time required to solve any differential equation as well as effort required to solve any differential equation. So it is basically a mathematical tool for analyzing the electric circuit. Just a second, I think. Yeah, so as I said, so Laplace transform is basically a tool that is used for analyzing any electric circuit. Okay, so there are several other tools such as Fourier transform is also available, but there are various limitation of using this Fourier transform, such as this Fourier transform we cannot be able to use for all kind of periodic signal, as well as this Fourier transform is only defined for stable system. Okay, so due to all these limitation we cannot be able to use this Fourier transform, okay, for solving any differential equation. So so basically all those limitations we can overcome by using this Laplace transform. Okay, so this Laplace transform we can use for all kind of periodic signals as well as unstable signal as well. Okay, so this is basically a motivation behind learning this Laplace transformation. Okay, so let us move ahead and see that how to find out a Laplace transformation if a signal is given to us. So let us suppose a continuous time signal, that is x of t, is given to us. Okay, so the Laplace transform of this signal x of t is defined by this equation. Okay, so x of t is basically defined as my integral minus infinite to infinite x of t into e raised to the power minus st dot dt. So s basically here is a complex. Okay, so x is basically a complex number. Okay, and which is defined as sigma plus j omega. Okay, so by using this equation we can easily transform a time domain signal into a frequency domain signal. So here s basically represents the complex frequency uh, parameter. Okay, so we can easily evaluate the Laplace transform by using this equation. So as we can see here that limit start from minus infinite and go till infinite. So that is why we can also uh, known this signal as a double-sided or bilateral Laplace transform. Okay, because here we integrate this signal from minus infinite to infinite, means we are covering both negative as well as positive half of the time. Okay, so this is known as double-sided or bilateral Laplace transform. However, uh, there are various physical systems or signals that are causal in nature basically. Okay, means it is defined only for t greater than 0. Okay, so there are several signal as well as system that are causal in nature. So for defining the Laplace transform for such a causal signal, we use this unilateral Laplace transform. Okay, so here we can see that limit start from 0 minus till infinite. Okay, so for uh, determining the bilateral Laplace transform we will use this x of s is equals to minus infinite to infinite x of t into e raised to the power minus st dot dt. Whereas for find out the uh, unilateral Laplace transform we will use this formula, which is where limit start from 0 minus and go till infinite x of t into e raised to the power minus st dot dt. Okay, so by using this formulas we can easily find out the unilateral as well as bilateral Laplace transform of any signal. Okay, so let us move ahead and see region of convergence. So this region of convergence is a very important parameter in case of Laplace transform. So basically what happened is like if suppose you have two signals. Okay, so there is a possibility like in Laplace transform that the value of Laplace transform will be same for both these signals. Okay, but uh, we can define a new parameter which is known as region of convergence. So basically this region of convergence states that it is a set of value over which Laplace transform defined. Okay, so this is basically known as region of convergence. So only that particular value of s the Laplace transform is defined. Okay, so that's how we can differentiate the Laplace transform of two different signals. Okay, so like I will take one example in the upcoming slide. So from there it will be clear to you. So before moving ahead, let us see what is the importance of ROC. So as I said, like for many signals, there may be a same expression of Laplace transform. Okay, for all these signals. Okay, so to distinguish the Laplace transform we define a region of convergence over which the Laplace transform is exist. Okay, so let us move ahead and take one example so that it will be clear to you. So here a signal this decaying exponential function is given to us, that is x of t is equals to e raised to the power minus at into ut. Okay, this signal is given to us and now we have to find out the bilateral Laplace transform. So as we know that Laplace transform x of s is defined as integral minus infinite to infinite e raised to the power minus at u of t into e raised to the power minus st dot dt. So now here ut is given to us in the signal. So as we know that ut, which is the unit impulse function, okay, unit impulse signal, let us say, so it start from 0 and go till infinite. Okay, so that's why we will take here limit start from 0 to infinite e raised to the power minus s plus a into t dot dt. So now we can evaluate this integral. So once you evaluate, you will get minus 1 over s plus a into e raised to the power minus s plus at, or and limit from 0 to infinite. Okay, so from here we can see that the this integral is written as minus 1 over s plus a in bracket e raised to the power minus infinite minus e raised to the power 0. Okay, so here yeah, one more thing, here we can directly s plus a into infinite. Okay, so from here we can see that this term, the value of this term, that is e raised to the power, will be equals to 1, whereas so this is basically a finite value. So to make this value, that is e raised to the power minus s plus a into t be 0. Okay, so what is needed, like s plus a, that is real part of s plus a, should be greater than 0, means it should be positive value, then only this e raised to the power minus infinite will be tends to 0. Okay, means it will be a finite value. Okay, so from here we can say that real part of s plus a will be greater than 0. So now if we will solve it, so real part of s will be greater than minus a. Okay, so this defines the region of convergence for which the Laplace transform of this function is evaluated. Okay, so as we know that e raised to the power, yeah,
Hello, sir.
yes, yes,
Here, one assumption we are making: A is greater than zero, right?
no, not a is
A.
greater than 0, that is s plus a is greater than 0, means this term, this whole term will be positive because t is
Okay, okay,
positive here. Yeah,
okay, okay.
yeah,
Whole term S plus. Okay, sir.
okay. So this defines basically the region of convergence, and that's how we can calculate the region of convergence for other signals as well. So now if we will evaluate this, so this will be equals to minus 1 over s plus a into uh, this will be 0 minus 1. So the overall Laplace transform of this function will be equals to s plus a. Okay, so uh, here it is written like s x of s is equals to 1 over s plus a for real part of s will be greater than minus a. So this basically defines the region of convergence uh, over which this Laplace transform is evaluated, and apart from this region of convergence, that is real part of s will be less than equals to minus a, this Laplace transform is undefined. Okay, so that's how we can calculate the Laplace transform of any signal. So here we can see that the plot of this e raised to the power minus 80 into ut is plotted here, which is a exponentially decaying function. Okay, and the corresponding region of conversion is also shown here. So here we can see that uh, this is a minus a, and greater than this minus a, the range of values of s, we can define the this Laplace transform, means only for this region we can define the Laplace transform, and apart from that, like here we cannot define the Laplace transform for this signal. Okay, so let us move ahead and see the next example. So here I am just replacing this previous signal, that is e raised to the power minus at into ut, with some other signal, that is minus e raised to the power minus at into u of minus t. Okay, so now we can see that these two signals are different. Even we can plot this signal, so after plotting you will get this kind of signal, like here it is shown. Okay, so this correspond to the plot of this signal, that is gt is equals to minus e raised to the power minus et into u of minus t. Okay, so now let us evaluate this Laplace transform for this integral, sorry, for this signal. So g of s is defined as minus infinite to infinite. mm, yeah, so we will put this, so let me solve this here. Yeah, so g of s is basically defined as minus infinite to infinite g of t into e raised to the power minus st dot dt. Okay, so now we can put the value of gt from this equation. So here we have put the value of gt into this exponential term which is present in the formula, that is e raised to the power minus st dot dt. So so from here we can see that this u of minus t is basically defined for negative value of t. Okay, so here is the u of minus t. Okay, so from here we can see that it is defined for negative value of t. That's why we will take limit from minus infinite to 0. Okay, so once you put this limit, uh, you will get uh, this expression, that is integral minus infinite to 0 e raised to the power minus s plus a into t dot dt. Okay, so now once you take the integral of this equation, you will get, yeah, let me solve this, minus 1 over s plus a into e raised to the power minus s plus a into t. Yeah, 1 minus will be come from this. Okay, e raised to the power minus s plus a, so this minus and minus will cancel and limit start from minus infinite to 0. Okay, so from here we can see that this is equals to 1 over s plus a e raised to the power minus s plus a into 0 minus e raised to the power minus s plus a into minus infinite. Okay, so from here we can say that to make this Laplace transform to be a unique value, okay, this term will be equals to 1. Basically this term will be equals to 1, whereas this term will be goes to 0 once s plus a, or the real part of s plus a, will be less than 0, means it should be negative, because here minus and minus will cancel out, so this becomes e raised to the power s plus a into infinite. So to make this e raised to the power, this term basically tends to 0, we have to make real part of s plus a should be negative. Okay, so from here, just a moment. Yeah, so real part of s here should be less than minus a. Okay, so this basically defined the reason of convergence for this function. So once you put this real part of s plus a should be negative in this expression, so you will get the Laplace transform of s 1 over s plus a. So from this we can see that the Laplace transform for this signal g of s will be defined as 1 over s plus a for real part of s will be less than minus a, and undefined once it will be greater than or equals to minus a. So these two from these two examples we can see that here the value of Laplace transform or the expression of Laplace transform for these two signals are same. However, the region of convergence is different. Okay, so that's how we can differentiate the Laplace transform of these two signals. Okay, so like here region of convergence is plotted. So here the range of value of s over which this Laplace transform is defined is this one. Okay, whereas in the previous solution the region of convergence is this one. Okay, so that's how we can make or say differentiate between the Laplace transform of these two signals. Okay, which is defined here in the examples. Okay, so I hope this example is clear to you, and if you have any doubt then please ask.
Sir,
Yes.
the previous example XT,
Yeah.
actually the region of convergence is inverse, right? So it is on the right hand side, but
Hmm.
this one is on the left hand side.
Yes, yes.
Yeah. So, for example, if there is a function which combines xt plus gt,
Uh-huh.
so there is no Laplace transform. There is,
No, if there are a intersection of the Laplace, sorry, region of convergence is exist, then only Laplace transform will exist. So
yeah,
let us
yeah.
suppose there is a yeah, let me please remove this once. Just a minute. Yeah, so like if suppose you have a signal which is basically a combination of two signal x1 of t plus x2 of t. Okay, so if the region of convergence corresponding to this x1 is r1, let us suppose, and this region of convergence corresponding to this x2 is r2. Okay, so if you plot this region of convergence, so here let us say uh, real part of s will be greater than r1, and here real part of s will be less than r2. Okay, so if suppose here is the r1. Okay, so for that region of convergence is this one, whereas for the second x2 the region of convergence is this one. Okay, this is r2. Okay, so Laplace transform is only defined only for this region where the intersection of these two signals will exist. Okay, and if yes,
Yes, sir. I got it.
yeah,
Just I am saying an hypothetical question. The
yes, yes,
previous problem, that xt and plus gt, if you
hmm,
combine,
hmm,
okay, some pt is equal to xt plus gt,
g g,
then the both are disjoint. So the Laplace should not exist.
yes, yes. In that case, Laplace will not exist.
Okay. Okay. Thank you. Thank you.
Yes. Any other doubt? Okay, so let us move ahead and see some of the uh, properties of region of convergence. So the first property states that region of convergence, yeah, region of convergence of x of s consists of strip parallel to j omega axis. So like in this example as well, we have seen that region of convergence start from let us say minus a, so it is basically a line that is parallel to the j omega axis. So here this imaginary of s is basically j omega. Okay, so the region of convergence is basically a line which is always be a parallel to the j omega axis. Okay, so this is basically the first property of region of convergence. So the second property of this region of convergence states that ROC of a rational Laplace transform should not contain any pole. Okay, so basically once you define Laplace transform of any signal, so let us say this is basically a Laplace transform of any signal. So this Laplace transform basically defined in terms of in terms of basically uh, like rational function s plus b s plus c. Okay, so here s is equals to minus a denotes the zeros, whereas s is equals to minus b and minus c are the poles of x of s. Okay, so here the second property states that the region of convergence will not should not contain any poles. Okay, so if suppose we will plot the region of convergence corresponding to this. Okay, so there has two poles, that is minus b minus c. So let us say it is minus b and it is minus c. So this region, there should be three region, or say region of convergence for this uh, Laplace transform. One is the, yeah, one is this one. Okay, the second one is this one, and the third one is this one. Okay, from here we can see that for all the three region, we are not basically, yeah, here we are not considering the poles. Okay, apart from these poles we are considering the region. So that's what this property states. Okay, that the region of convergence should not contains any pole. Okay, because at that pole the value of this x of s will be infinite. It is not defined at the pole, so that's why we are excluding this pole. Okay, so now the third property is ROC is entire s plane for the finite duration x of t. So let us suppose here is the signal x of t. Okay, which is defined only for finite value of time from b to c. Okay, and here is the amplitude, let us say. Okay, so for this finite duration signal, the ROC will be, means once you plot this in frequency or Laplace domain, so the ROC will be entire s plane. Okay, entire s plane means it is defined for all the values of s. For all values of s, this x of s is defined. So that's why here ROC is considered as entire s plane. Okay, means for all value of s, this x of s will converge. Okay, now the third property states that for the right-handed signal, the ROC is basically greater than or equals to sigma 1. Okay, so let me erase this first. Yeah. So first of all, let us see what is basically a right-sided signal. So a signal x of t, which is equals to 0 for t, let us suppose t less than t naught. So it is basically a right-sided signal. So like here it is 0 for t less than t naught, and for t greater than t naught it is defined. So this is basically a right-sided signal. So here the ROC is basically defined for this kind of signal, that is right-sided signal. ROC is basically real part of s will be greater than t naught. Okay, so basically this this is basically stated by this property of ROC, that is for right sided signal contains the line uh, real part of s is equals to sigma 1, then real part of s will be greater than sigma 1. Okay, similarly for the left sided signal, okay, which contains a line that is real part of s is equals to sigma 1, the ROC is defined as real part of s will be less than sigma 1. Okay, whereas the last property states that the ROC of the two-sided signal, like as uh, question asked by one of the listener, like if suppose we have a signal which is composed of summation of two signals, so for those kind of signal, ROC is basically defined as uh, strips. Okay, means I want to say, like here, let us say x of s, and it contains two strips. Okay, so ROC is basically defined as intersection of these two strips. So for double sided signal, the line contains the line real part of s is equals to sigma naught, then ROC will contains a strip which includes the line. Okay, so these are the some important properties of region of convergence. So let us move ahead and solve a problem so that this Laplace transform will be clear to you. So here a question is given to us, like we have to calculate a unilateral Laplace transform for the function given to us. So function is given to us like x of t is equals to 2t once when t belongs from 0 to 1. Okay, defined and it is equals to 2 once t is in the range of 1 to 2. So let us first plot this signal x 7t is so this is 0, this is 1. Okay, so this will be 2, and from 1 to 2 the value of this signal is 2. Okay, and between 0 to 1 this is a triangular signal. Okay, so that's how we can plot this signal. So from here we can see that it is a finite duration signal. So basically here we have to calculate the Laplace transform of this signal. So Laplace transform, as we know, that it is defined as x of s is equals to minus infinite to infinite, but here as it is mentioned in the problem that we have to calculate unilateral Laplace transform, so that's why I'm considering the limit of integration is from 0 to infinite x of t into e raised to the power minus st dot dt. So this will be equals to yeah, this will be equals to 2t into e raised to the power minus st dot dt, limit from 0 to 1 plus 1 to 2 e raised to the power minus st dot dt. Okay, so now we can evaluate this integral. So to evaluate this integral we will use integral by parts. Okay, so here I am defining like this is my first part, this is my second part. Okay, so by using integral by parts we can evaluate this integral. So like this is 2, this is first function, uh, yeah, first function into sorry, this is basically my first function, this is my second function. So integral of second function means minus st over minus s minus integral of d by dt of first function which is t. So this will be equals to 1 into e raised to the power minus st over minus s dot dt. Okay, so we can evaluate this integral, and the second integral is e raised to the power minus st over minus s, and the limit is from 1 to 2. Here for the first integral limit is from 0 to 1 basically. Okay, so once you evaluate this integral, uh, yeah, you will get this expression. Okay, you will get this expression once you evaluate this integral. So I'm leaving this part to you. Okay, you can evaluate it by yourself. So from here we can see that at s is equals to 0 this x of s is not defined. Okay, this x of s is not defined. So as we can see here, this s term is basically coming from this expression, that is e raised to the power minus st. So for evaluating the value of x of 0, what we will do, we will put the value of s in this expression as 0. So the integral is now becomes 0 to infinite x of t into e raised to the power minus 0 will be equals to 1 dot dt. So by using this we can evaluate the value of x of 0. So that's what here we are calculating. We are just putting the e raised to the power minus st here. S is 0. Okay, so this will be equals to 1. So the integral becomes 0 to infinite x of t dot dt, so that you can calculate. So once you calculate this integral, the value you will get at s is equals to 0 is 3. So from here we can see that for s is equals to 0, the calculated Laplace transform is 3, whereas for s not equals to 0, this is the Laplace transform. Okay, so from here we can see that for finite duration signal, the Laplace transform is defined for the entire s plane. Okay, for the entire s plane means for all value of s, this Laplace transform converge. Okay, that's why here in the property it is written that yeah, for finite duration signal x of t, the ROC will be entire s plane, because for all value of s, this Laplace transform will converge. Okay, so I hope this problem is clear to you. So if you have any doubt in this problem, then please ask. Okay, so let us move ahead. Uh, that is inverse Laplace transform. So the next topic is inverse Laplace transform. So in the previous topic, we have seen that a time domain signal x of t is basically given to us. So now, for analysis of this signal, what we are doing, we basically convert this time domain signal into frequency domain signal, or say Laplace domain signal. Okay, so the inverse problem states that if suppose x of s is given to us, so can we basically determine that what is basically the signal uh, which basically give us this Laplace, this kind of Laplace transform. So such kind of inverse problem is basically known as inverse Laplace transform. So this is basically a synthesis problem where x of s is given to us. Okay, on the basis of that we are calculating the input signal, that is x of t. So this is basically a kind of synthesis signal. Say, sorry, synthesis problem. Okay, so so this inverse Laplace transform states that for a given x of s, the inverse Laplace transform is defined as x of t is equals to minus 1 over 2 pi j integral sigma minus j omega. Omega means infinite to sigma minus j omega. Here I think some mistake is there. This limit should be minus infinite to infinite x of s e raised to the power st dot ds. Okay, so this x of t is basically defined as 1 over 2 pi j integral minus infinite to infinite x of s e raised to the power xt dot ds. Okay, so by using this expression we can obtain basically the input signal for a particular Laplace transform. Okay, but the problem here by using this expression is that it is very complex to evaluate the integral of this Laplace transform. Means for several complex uh, Laplace transforms, we cannot evaluate this integral. So we will use basically a simpler method where by using partial fraction, okay, by using partial fraction we will break this Laplace transform into known Laplace transform of known functions. Okay, so by using this partial uh, partial fraction method, we can basically evaluate the inverse Laplace transform. So we will use this method instead of using uh, this formula for evaluating the value of x of t. Okay, so let us take an example. So here a linear time invariant continuous system is given to us, that is h1s is equals to s plus 4 into s plus 5 divided by s square s plus 2 into s plus s minus 2. Okay, this system is given to us. Now calculate the impulse response if specified linear time invariant continuous system are causal. Okay, so first of all, this system is given to us and we have to calculate basically the impulse response. Okay, means yeah, this h of s is basically defined as y of s over s of s. Okay, so from previous lecture we have seen that impulse response basically the response of any system y of s once we provide impulse as the input, means delta t as the input to the system. So what output we will get, it is known as impulse response. Okay, so for uh, for impulse response, y of s will be same as h of s. Okay, because the value of x of s will be equals to 1. Okay, for delta function the Laplace transform will be equals to 1. Okay, so why I am saying this, so we can also calculate like x of s is equals to minus infinite to infinite delta of t into e raised to the power minus st dot dt. So as we know that delta is defined only for s is equals to 0. So for evaluating this integral, what we have to do, we have to just put this uh, s as 0, s as 0. So once you put, you will get this Laplace transform of delta function is equals to 1. So that's why y of s is same as h of s here. Okay, so now in the question it is it states that we have to uh, calculate the impulse response of the specified linear time invariant continuous time system. Okay, so basically here this h of h1s is same as y of s. Okay, so for evaluating the response in time domain, okay, means in time domain basically we have to calculate the response. Okay, so what we will,
Sir,
yes,
as I understand,
yes, yes.
the impulse response is nothing but inverse Laplace transform of h of s. H of t
Mm-hmm.
is the impulse response
Hmm.
that is same as inverse Laplace transform of h of s, right?
Yes, yes, it is same. I'm just saying like
The,
here we have to obtain the impulse response. Basically, what is basically an impulse response? It is defined only for a system once we provide impulse as a input. Okay, what response basically we are getting at the output? This basically defines the impulse response.
yes, that is notation is h of t.
Yes, yes, yes.
Yeah,
Yeah.
yeah.
So that
Okay.
what I am saying ki we have to
Okay.
calculate the impulse response in time domain. Okay.
Yeah. So basically, so mathematically, it is nothing but inverse Laplace transform of h of s.
Yes.
Okay. Okay.
Yeah.
Right.
So basically, if you want, you can use this expression. Okay. for evaluating h of t. But the thing is, to evaluate this integral is sometimes very difficult. Okay, so to overcome this integration part, what we will do, we will use partial fraction method. Okay, where we will first calculate the partial fraction, means we will first express this complex function into uh, Laplace transform of some known functions. Okay, then by using this known function we will calculate or say evaluate the inverse Laplace transform. Okay, so this method is basically very easy for us to calculate the inverse Laplace transform as compared to this one. Any doubt?
Okay, sir. Go ahead, sir.
Okay, so yeah, so what we will do, we will first take partial fraction of this expression. So this partial fraction is defined as k1 over s plus k2 over s square plus k3 over s plus 2 plus k4 over s minus 2. Okay, so basically we have to evaluate this coefficient k1, k2, k3 and k4 because uh, we already know. Yeah, just a minute. So basically we already know that what is the uh, what is the inverse Laplace transform of 1 over s, what is the inverse Laplace transform of 1 over s square, what is the inverse Laplace transform of 1 over s plus 2, what is the inverse Laplace transform of s 1 over s minus 2. All this inverse Laplace transform we already know. Okay, so by using this we can easily evaluate the inverse Laplace transform of this impulse response. Okay, so we have to just calculate this value of k1, k2, k3 and k4. So for evaluating this is basically a mathematical process. This For finding out this k1, k2, k3, k4, you can find out this method in any mathematics book, engineering mathematics books. Okay, so from here we can calculate this value of k1, k2, k3 and k4. Okay, so once you calculate this, the value of k1 is equals to 1, sorry, minus 9 by 4, k2 will be equals to minus 5, k3 will be equals to minus 3 by 8, and k4 will be equals to 21 over 8. Okay, so I am leaving this exercise because it is a basic mathematics. You can calculate this by yourself. Okay, so I am not going deep into this uh, calculation part. Okay, and I am leaving this to you. So once you calculate this coefficient, you can put this value of coefficient in this expression. Okay, like here in this expression you can put the value of k1, k2, k3 and k4. Okay, so the final value of h1s is equals to minus 9 over 4s minus 5 over s square minus 3 over 8 s plus 2 plus 21 over 8 s minus 2. Okay, so now as we know that inverse Laplace transform of 1 over s will be equals to u of t, whereas 1 over s square will be equals to t into u of t. 1 over s plus 2 is basically e raised to the power minus 2t into ut, and 1 over s minus 2 e raised to the power 2t into ut. Okay, this integral is well known. Okay, and you can get this from any standard book of signals and system. Okay, so from there we can directly take the inverse Laplace transform, and once you take inverse Laplace transform, the final impulse response for this is defined as minus 9 by 4 minus 5t minus 3 by 8 e raised to the power minus 2t plus 21 over 8 e raised to the power 2t into ut. Okay, so this basically defines the impulse response, where I basically define the region of convergence for each and individual partial fractions. Okay, like here s will be greater than 0, here also s will be greater than 0, here s will be greater than minus 2, here s will be greater than 2, means all these are right sided signal.
Sir, how do we know it's the right sided, sir?
Yeah, basically here region of convergence is defined like for 1 over s minus 2, if you plot in the s plane, so here minus 2, so I am taking real part of s will be greater than minus 2, so this is basically a right sided signal. Okay,
Okay.
yeah, here also I mentioned like for right sided signal contains the line real part of s is equals to sigma 1, so the region of convergence will be greater than sigma 1. Okay, so that's how we can say that it is a right sided signal.
Okay, okay.
Okay, so for all these partial fractions, I am considering that it is a right sided signal, so that's why we are getting this expression. Okay, but if suppose I am considering left sided signal, okay, so here real part of s will be less than 0, real part of s will be less than 0, here real part of s will be less than minus 2, and here real part of s will be less than 2. Okay, so once you change the region of convergence, so the expression will change. Okay, so for this left-handed signal, the inverse Laplace transform of 1 over s will be minus u of minus t, 1 over s square will be minus t into u of minus t, 1 over s plus 2 will be minus e raised to the power minus 2t into u of minus t, and this 1 over s minus 2 will be equal to minus e raised to the power 2t into u of minus t. Okay, so from here we can see that once we change the region of convergence, or once we change the yeah, region of convergence, so the signal will also change accordingly.
Sir, here region of convergence will be given, right, as part of the problem?
Yeah, it is given, but here I am
Yeah.
just showing you that if region of convergence is changing, so corresponding signal will change.
Okay, but in actual
Yeah,
problems, when we have to
yes, yes,
compute inverse transform,
haha,
they give the region of convergence,
yes, yes,
right? Then only.
yes, yes, then only you can uniquely define the inverse Laplace transform, otherwise inverse Laplace transform will be different for different region of convergence.
Okay, okay. So for causal, we can immediately find out region of convergence. If it is specified as causal,
Yes, yes, yes,
then yeah.
yes,
So here it is non-causal. That's why it is less than zero,
mm-hmm.
real value of it.
Yes.
Okay, okay, okay.
Okay, so this is the same kind of problem that I am leaving to you because of time constraint. Okay, so if later time permit, I will come to this problem and solve this problem for you. So I am leaving this problem for time being. So let us move ahead and see some important properties of Laplace transform. Okay, so the first property is the linearity property. Okay, so if x1 and x2 are the two signal with Laplace transform x1 x and x2 x, and region of convergence of these two Laplace transform is defined as r1 and r2 respectively, so the Laplace transform of linear combination of x1 and x2 is given as, uh, let us suppose this is the linear combination of x1 and x2 s. So the Laplace transform of this linear combination is defined as a1 x1s plus a2 x2s, where a1 and a2 are the arbitrary constant. So as a proof, we can take this as an input signal. So from the basic formula of Laplace transform, we will put x of t as a1 x1t plus a2 x2t here. Okay, so here we can see that once you multiply this term inside this these two linear combination of signals, so uh, the overall Laplace transform is basically defined as a1 x1s plus a2 x2s. Okay, so this is a proof that if a signal is given to you which is a linear combination of two different signal, so the corresponding Laplace transform is basically a linear combination of individual Laplace transform, provided that region of convergence is basically a intersection of r1 and r2. Means region of convergence is basically a intersection of region of convergence of these two signals. Okay, so this basically a linearity property of a Laplace transform. So the second property is the time shifting property. So if a signal x of t is given to us, so the Laplace transform, if a signal x of t is given to us, okay, with a region of convergence is r, so the Laplace transform of x of t minus t naught is given as Laplace transform of x of t minus t naught is given as e raised to the power minus s t naught into x of t. It means that if you provide delay in a time, then in in Laplace domain you will multiply this x of s with e raised to the power minus s t naught. Okay, so this basically defines the Laplace transform of shifted function. Okay, and one more thing is like here region of convergence is same as x of s. So as a proof, we can take Laplace transform of x of t minus t naught. So here I am directly putting x of t as x of t minus t naught e raised to the power minus st dot dt. So for solving this integral, what I am doing, I am substituting t minus t naught as a tau. Okay, and once you take derivative of this tau, so d tau will be equals to dt. Okay, and the limit of integration will remains the same, so this will be equals to minus infinite to infinite x of tau into e raised to the power minus s t plus t naught into d tau. Okay, so from here we can take e raised to the power minus s t naught as a common. Okay, and this basically denotes the expression of Laplace transform. So that's why we are stating here that x of Laplace transform of x of t minus t naught is equals to e raised to the power minus s t naught into x of s. Okay, so the third property is the shifting in the s domain. Okay, so if a signal x of t is given to us with a region of convergence r, so the Laplace transform of e raised to the power s naught t into x of t is given as x of s minus s naught. Okay, so we can also prove here uh, the Laplace transform of this function. So this is defined as Laplace transform of e raised to the power s naught t into x of t. So this will be equals to minus infinite to infinite e raised to the power s naught t into x of t into e raised to the power minus st dot dt. So from here we can take x of t into e raised to the power minus s naught into t dot dt. Okay, so now we can see here that here the parameter is changed. Here the parameter is defined as s minus s naught instead of s, like the expression of x of s is for any signal x of t is defined as x of t into e raised to the power minus st dot dt. Okay, so here the parameter is s, but for this expression the uh, yeah, the parameter is change, which is equals to s minus s naught. Okay, so that's why here uh, the Laplace transform is defined as x of s minus s naught. Okay, and the region of convergence for this uh, Laplace transform will be equals to real part of uh, means region of convergence of the signal x of t plus real part of s naught. Here this should be s naught. Okay, so this basically defines the region of convergence of the new signal. Okay, so let us move ahead and see the time scaling property. So the same signal x of t is given to us, region of convergence is also same, but now we have to calculate the Laplace transform of x of at, where a is a constant. Okay, so we have to evaluate the Laplace transform of this signal. Okay, so this is basically defined as 1 over a x of s by a. So this defines the Laplace transform of time scaling signal. Okay, here the region of convergence is also change, which is equals to r over a. Okay, so let us prove this property as well. So Laplace transform of x of at, we have to evaluate the Laplace transform of this signal. So we will put here x of t as x of at. Okay, so to evaluate this integral we will substitute at as a tau. Okay, so now uh, from here d tau will be equals to a into dt. So dt is basically uh, equals to d tau over a. Okay, so from here we can replace the parameter. Okay, and also change the limit of integration. Okay, so once you calculate this integral you will get the Laplace transform of time scaling function will be equals to 1 over a x of s over a. Okay, so all the application of all these problem we will see later in this slide. Okay, so let us see the first problem here based on the properties that we have seen. So like in one of the previous problem we have seen that for this signal, we have evaluated the Laplace transform which is defined here. Okay, so now we have to basically evaluate the Laplace transform of a new signal which is given here. Okay, so from here we can see that if we will compare these two signal, these two plots, so from here we can see that this h of t is basically time expansion of this signal x of t. Okay, it is expanded in time. Also the amplitude is changed here. Okay, here the maximum value is 2 whereas here the maximum value is 3. Okay, so this h of t is basically both time scaling as well as amplitude scaling of x of t. Okay, so the new uh, signal h of t is defined in terms of x of t as 3 by 2 into x of t by 2. Okay, so from our first class we have seen signal transformation. So from there uh, we can uh, put h of t as 3 by 2 x of t by 2. Okay, so that's how we can make a relationship between these two signals. Okay, so as we know the Laplace transform of x of t, which is given here, so by using this scaling property now we have to evaluate the Laplace transform of h of t. Okay, so this we can also write as 1.5 x of 0.5 into t. Okay, so like Laplace transform of this signal is basically defined as 1 over zero point 0.5 into 1.5 x of s over zero point 0.5. Okay, so once you evaluate, this is equals to 3 x of 2s. Okay, so x of s is basically given to us. So here what we have to do, we have to multiply the amplitude by 3 and also replace the parameter s with 2s, so as to evaluate h of s. Okay, so that what I am doing here, I am just multiplying the amplitude by 3. Okay, and replace the parameter s here as 2s. So once you put once you replace the parameter and put the amplitude or multiply the amplitude by factor 3, the final the final uh, Laplace transform of this signal is given as this. Okay, and also here like in the uh, previous problem, yeah, this one. Okay, so here the ROC is entire as plane. Okay, so ROC here also, I'm sorry, yeah, the here also the ROC is r over r over 2. Okay, which is basically entire S plane. Here all ROC will also be entire S plane. So if any doubt in this problem, then please ask. Any doubt? Okay, so let us move ahead and see the next property. So the next property is division by t. So if signal x of t is given to us, uh, and the region of convergence is, let us say it is equals to r. So we have to define the Laplace transform x of s. Okay, uh, once this signal is x of t by t, so corresponding to this signal we have to evaluate the Laplace transform. Okay, so for evaluating this Laplace transform of this signal, we have to use this property, that is s integral s to infinite x of u dot du. Okay, by using this property we can easily evaluate this modified signal, which is equals to x of t over t. Okay, so let us suppose this signal sine of t by t is given to us, and we have to evaluate the Laplace transform of this signal. So for evaluating this Laplace transform of this signal, what we have to do, we will use this property. Okay, so here x of t is basically defined as sine of t. Okay, so x of s is equals to, yeah, omega over s square plus omega square. So the value of omega is 1 here. So that's why x of s will be equals to 1 over s square plus 1. Okay. So this x of s is given to us. Now for evaluating Laplace transform of x of t over t, we will use this property, that is integral s to infinite 1 over s square plus 1, or you can change the parameter here, dot du. Okay, so this will be equals to tan inverse u, and the limit is from s to infinite, so this basically equals to pi by 2 minus tan inverse s. Okay, so that's how we can use this property, that is division by t, for evaluating the Laplace transform of such kind of signal. So now the next property is time differentiation. Okay, so here if suppose a signal x of t is given to us, and we have to evaluate the Laplace transform of the signal d by dt. So for evaluating this Laplace transform of this kind of signal, we will use this property that is known as time differentiation. Okay, so the Laplace transform of this signal is basically defined as s x of s minus x of 0 minus. Okay, basically this defines the initial condition. Okay, so by using this property we can evaluate the Laplace transform of differentiation function. Okay, so as a proof, let us suppose we have to evaluate the Laplace transform of this signal dx by dt. So we will use this expression, that is uh, yeah, 0 to infinite d by dt of x into e raised to the power minus st dot dt. Okay, so for evaluating this expression we have to use integral by parts. Okay, so here uh, I will take this d by dt as a first function, and this e raised to the power minus st as the second function from islets. Okay, so once you evaluate this integral, you will get e raised to the power minus st into integral of d by dt of x. So this will be equals to xt minus integral of e raised to the power minus st d by dt of, okay, so basically this will be d by dt, so this is minus s e raised to the power minus st into, yeah, integral of second function. So this, just a moment, 0 to infinite first function into integral of second function minus integral d by dt of first function minus integral of second function. Okay, so here this will be equals to first function, that is x of t, into integral minus st into minus s. Yeah, so you can evaluate this integral, and once you put the value of limit, okay, in this expression, so you will get the Laplace transform as Laplace transform of dx by dt will be equals to s x of s plus x of 0 minus. Okay, so you will get this expression once you apply the limit of integration here. Okay, so here is the question. Okay, uh, corresponding to the time differentiation property of the Laplace transform. Okay, so here basically uh, ut is given to us, and we know that corresponding to ut, that is unit impulse function, the Laplace transform is defined as 1 over s, and here the region of convergence will be great, as real part of s will be greater than 0. So now we have to evaluate the Laplace transform for the impulse function. Okay, so as we know that uh, impulse function is basically defined as d by dt of ut. Okay, so it means that we have to use here the uh, differentiation property so as to evaluate the Laplace transform of impulse function. Okay, so we will use this property. So as we know that du by dt, Laplace transform of this du by dt is defined as s x of s minus x of 0 minus. Okay, so corresponding to ut, the x of s is equal to 1 over s minus u of 0 minus. Okay, so this will be equals to 1 minus u of 0 minus. Okay, so as we know that u of t is defined as for t greater than 0, u of t is basically defined as for t greater than 0. Okay, so the value of u of 0 minus will be equals to 0. So that's why the im- uh, the Laplace transform of delta function will be equals to 1. So by using this differential property, we evaluated the Laplace transform of delta function. Okay, as the unit impulse function is given to us. Okay, so the next property is time integration. So time integration property states that if suppose x of s is given to us corresponding to this x of t is given to us corresponding to this x of t, the Laplace transform is x of s. Okay, so the uh, unilateral Laplace transform is defined as 0 to t x of tau dot d tau is defined as x of s over s for unilateral Laplace transform. Okay, whereas for bilateral Laplace transform, this time integration is defined as minus infinite to t x of tau dot d tau is equals to x of s over s plus 1 over s integral minus infinite to 0 minus x of tau dot d tau. So this correspond to the initial value. Okay, so for unilateral Laplace transform, this initial value is not given, this will be equals to 0. So that's why for unilateral Laplace transform, the uh, Laplace transform of time integration is defined as x of s over s, whereas for bilateral Laplace transform, the Laplace transform of time integration signal is given as x of s over s plus 1 over s integral minus infinite to 0 x of tau dot d tau. Okay, so here is the problem based on the time integration property of the Laplace transform. So here uh, cos of omega t is the signal and the corresponding Laplace transform is given to us, that is s over s square plus omega square. Okay, so now we have to derive the Laplace transform of sine of omega naught t into ut. Okay, so from here we can see that ut is given to us, so it is a unilateral Laplace transform problem. Okay, so here we have to use this property, that is 0 to t x of tau dot d tau will be equals to x of s over s. Okay, so here x of tau is basically cos of omega naught t. So this will be equals to 0 to t cos of omega naught t dot d let us say it's a tau, d tau is equals to 1 over s into s over s square plus omega naught square. Okay, so once you evaluate this integral, so this will be equals to sine of omega naught tau over omega naught. Okay, and limit of integration will be equals to, yeah, 0 to t, and this will be equals to, right hand side will be equals to 1 over s square plus omega naught square. Okay, so once you put the limit of integration here, this will be equals to 1 over omega into sine of omega naught t, 1 over s square plus omega naught square. So sine of omega naught t will be equals to omega naught over s square plus omega naught square. Okay, so this basically, this is that is how we can use the time integration property so as to evaluate Laplace transform of sine of omega naught t, as cos of omega naught t function is given to us. Okay, so by using time integration property, we have evaluated the Laplace transform of sine omega naught t here. Similarly, we there are another property which is time convolution or S-plane convolution. So if suppose two signal x1t and x2t is given to us, okay, having Laplace transform x1s x2s and region of convergence r1 and r2. So if suppose we have to evaluate the uh, Laplace transform of convolution of these two signal, so in Laplace domain, the uh, Laplace transform is defined as x1s dot x2s. Okay, means convolution in time will be equals to multiplication in Laplace. Okay, and also the region of convergence will be equals to r1 in intersection of r2. Okay, so that is how we can evaluate the uh, convolution of sorry, Laplace transform of convolution of two signals. And if suppose uh, uh, this we will multiply uh, these two signals instead of convolution, so after multiplication we will get 1 over 2 pi j. In Laplace transform we will get 1 over 2 pi j x1 of s convolution of x2 of s. Okay, so this correspond to the time convolution, whereas this correspond to the s-plane convolution. Okay, because here the convolution is basically uh, mm, provided on the s-plane, means Laplace domain. Okay, so that's why it is known as s-plane convolution. So here is a problem which is basically based on the time convolution. Okay, so a continuous time input signal x of t is given to us, which is applied to a linear time invariant system with impulse response h of t is equals to e raised to the power minus 2t into ut. So now we have to determine the output produced by the system using the Laplace transform method. So here, if suppose this is the system h of t, okay, having impulse response h of t, so now we are applying a signal x of t at the input to this system. Now we have to evaluate the output of this system, okay, using this Laplace transform. So as we know from the previous class that the output of this system is basically defined as the convolution of input signal and impulse response of this system. Okay, so the first process is either you take the convolution of these two signal. Okay, so like in the previous class we have seen, like it is defined as minus infinite to infinite x of tau h of t minus tau dot d tau. So either by evaluating this integration you can evaluate the output y of t, or what we will do, we will first convert these signals into uh, Laplace domain, and then we will evaluate the output. So here we will use the second method, we will first uh, convert this time domain signal in the frequency domain, and then we will evaluate the output of this system. Okay, so the x of t which is given to us, that is minus e raised to the power minus t into u of t. So the corresponding Laplace transform is defined as 1 over s plus 1. Okay, and the region of convergence is defined as real part of s will be greater than minus 1, whereas for the second signal h of t e raised to the power minus 2t into ut, the h of s is defined as 1 over s plus 2. Okay, here real part of s will be greater than minus 2. Okay, so the output in Laplace domain is defined as h of s into x of s. Okay, so h of s is 1 over s plus 2 into x of s is 1 over s plus 1. Okay, so this is basically y of s. So now we will use the partial fraction method so as to break this uh, y of s into a Laplace transform of known functions. Okay, so like here I am using partial fraction method. So once I use the partial fraction method, I basically divide this y of s into two basically known Laplace transforms, that is 1 over s plus 1 minus 1 over s plus 2. Okay, here region of convergence is also I am taking same as this one. Okay, so from here, if I am considering it is a right-handed side, okay, right-handed signal. Okay, so in that case, uh, the value of this Laplace transform is e raised to the power minus t into u of t, whereas for this integral this will be equals to e raised to the power minus 2t into u of t. So now once you put the value of this uh, uh, signal here, you will get y of t is equals to e raised to the power minus t minus e raised to the power minus 2t into ut. So this is basically represents the output of the system. Okay, which we have evaluated by using this Laplace transform method. So the next topic, the next property is the initial value and final value theorem. So initial value means if suppose a signal x of t is given to you, and for calculating the initial value, what you have to do, you have to put t as 0. Okay, because we consider here like t is equals to 0, at t is equals to 0 the signal will start, so this will act as a initial value problem. Okay, so once you put t is equals to 0 here, so this represent the initial value problem or initial value theorem. But if suppose corresponding to this xt signal x of s is given to you, so if I am saying that now you have to evaluate the uh, initial value corresponding to this x of s, so what you have to do, you will first calculate the x of t by using this x of s. Okay, so this will basically take a time. Okay, so to make this problem easy, what we will do, we will use initial value theorem. So initial value theorem states that x of 0 plus is equals to limit t tends to 0 plus x of t is equals to limit s tends to infinite s into x of s. Okay, so if x of s is given to you, and now I am saying to calculate the initial value of this x of s, so what you have to do, you have to just multiply this x of s by s, and then you have to uh, take limit s tends to infinite. So by calculating this, we can easily evaluate the initial value of this signal x of t. Similarly, for evaluating the final value, what we have to do here, at t we will put t is equal to infinite. Okay, so for evaluating final value, we will put t as infinite. So this will be equals to limit t tends to infinite x of t is equals to limit s tends to 0 s into x of s. So by using these theorems, we can easily evaluate the initial value and final value of any signal if suppose Laplace transform of these signals is given to us. Okay, so as an example, here Laplace transform of two signals, that is x1 t and x2 t, is given to us here. Okay, so by using this, we have to evaluate both the initial value and the final value of this function. Okay, so uh, i uh, as I discussed in this slide, like for evaluate the initial value for the first signal, that is x1 t, what you have to do, either put t tends to 0 plus. Okay, uh, but here for evaluating this expression, you have to first determine this signal x1 t, means in time domain you have to first evaluate the signal. So for saving time, what I am doing, I will use the expression of in Laplace domain. Okay, so this will be equals to limit s tends to infinite s into x1s. Okay, so here once you multiply s into x1s, so this s from both numerator and denominator will cancel each other, and this expression, once you put s is equals to infinite, this will be equals to 0. So this represent the initial value corresponding to this signal x1t. Whereas for evaluating the final value theorem, we have to put s is equals to 0 instead of placing s is equals to infinite here. So uh, once you basically uh, multiply this s into x, so this s from both numerator and denominator will cancel each other, and this will be equals to 3 over 1 1 into 2, which will be equals to 1.5. So this is the final value of this signal x1t. Similarly, we can calculate the initial value and final value of the second signal, that is x2t. So for calculating this initial value corresponding to this signal x2t, we will take s tends to infinite s into x2s. Okay, so from here, uh, yeah, you can take s square common, so this will be equals to 1 over 5 by s, and this will be equals to s cube, and yeah, this is 1 plus 5 over s plus 17 over s square plus 13 over s cube. Okay, so this will cancel. So now once you put s tends to infinite, so the value of this expression will be 0. So this basically represents the initial value of signal x2t. Okay, similarly for evaluating the final value, you have to put s is equals to 0 instead of placing s is equals to infinite like in initial value problem. So once you put s is equals to 0, the final value will also come to 0. Okay, so by using this initial value and final value theorem, we can evaluate uh, the initial value and final value in Laplace domain. Okay, so the next topic is stable and causal linear time invariant system. So for causal system, we know that the Laplace transfer function corresponds to the right sided system. Okay, means the region of convergence is basically region of convergence should be right sided. Okay, if region of convergence is right sided, then we can say that this function is basically a causal function. Okay, whereas for evaluating the stability, we have to test the roots. Okay, roots of this transfer function. Okay, let us suppose h of s is given to us as a naught s to the power m plus a1 s to the power m minus 1 plus a2 s to the power m minus 2 plus dot 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 plus am over b naught s to the power n plus b1 s to the power n minus 1 plus b2 s to the power n minus 2 plus dot 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 plus bn. Okay, so such kind of transfer function is given to us. So first of all we have to evaluate the poles, means corresponding to the denominator function we have to evaluate the roots. Okay, so the roots of this denominator function basically represent the pole of the transfer function. Okay, so once we evaluate the poles of this transfer function, so by evaluating that in which region basically poles are lying, if poles are lying in the negative part of S plane, like here. Okay, if poles are lying in the negative part of S plane, so we can say that this system is a stable system. And if it lies in the, yeah, it lies in the right hand side of the S plane, means positive side of the S plane, then it is unstable system. Okay, this is a stable system. So uh, so let us see this stability uh, checking by using this uh, problem. Okay, so here h1s is given to us, that is s plus 4 into s plus 5 over s square into s plus 2 into s minus 2. So for this we have to check the stability, whether this system is stable or not. So for that we have to evaluate first the pole. Okay, so pole of this transfer function is basically s is equals to 0, s is equals to 2 and s is equals to minus 2. Okay, so once you plot the poles of this transfer function, so two pole will come here at s is equals to 0, one pole will come here at s is equals to minus 2, whereas the another pole will come here at s is equals to 2. So as we can see here that one pole is lying in the positive half of the S plane. So that's why this system is basically an unstable system. Okay, so this system is unstable system. Whereas corresponding to this uh, system H2S, once you evaluate the poles, means you have to take the denominator function and find its root. Okay, so once you uh, find the root of this polynomial function, so you will get s is equals to minus 1 and s is equals to minus 2 plus minus j3. Okay, so once you plot this in the complex x plane, so one root will come here. Okay, the another two root will come here. Okay, it means that it lies on the negative half of S plane. So that's why this system is basically a stable system. Okay, so this is basically a stable system.